Today we're going to continue on talking about how it is that populations disperse themselves across the landscapes. Look at this image here, for example. We have a forested landscape, but also it's broken up into segments by intervening areas of farm field and pond and so on. And so one might ask, how does this breaking up of habitats influence how it is that populations are able to maintain themselves and spread from one place to another? Let's look a little bit more closely at the opposite extremes of this situation. We're looking here at an aerial true color photo of a patch of landscape in New England. And you'll notice that most of that landscape is forested. All those little bumpy things you see there are all tops of trees, except about a little left of center in the field of view we see a river snaking through the area, and there it looks different. There it's got some marshland along it. So we have this natural break in this forest cover, but aside from that, it is pretty much uniform, contiguous forest. So one type of habitat, one general type of habitat at least, throughout this whole area. Now let's compare that area with this one. Notice that in the foreground there's a little patch of woodland, and in the midground there's a ribbon of woodland along a pond and a field. And the field goes around the pond, and then in the background there are a couple of little groups of trees, and then way in the background there's an area of fairly continuous forest. So these observations lead to asking some interesting questions. How is it, let's say, for some animal that lives in woodland, how would these two areas compare in terms of how its populations might be able to sustain themselves, and how would that influence how it was able to disperse from one place to another? So what I'm getting at here is this model of plant and animal dispersal referred to as the source sink model. And what this model assumes is that the habitats that these organisms live in differ in quality, and that higher quality habitats are likely to be what are referred to as source habitats, because the organisms that live within them are capable of producing a surplus of young every year. And in contrast, poorer quality habitats are referred to as sink habitats, because although some of the same species might live in them, it's likely that populations are unable to maintain themselves, and so the only way those species stay in these poorer quality habitats is by immigration from source habitats. So in the case of forest animals and forest plants for that matter, often large contiguous tracts are thought of as source habitats, whereas fragmented forests often appear to serve as sink habitats. So let's consider this little guy right here as an example of all that. This is the ovenbird, which in southern New England, where I've studied them, is the most abundant bird in extensive forest tracts. However, it is a ground nester, and that makes it vulnerable to certain kinds of predators. In large contiguous tracts, it seems to have the advantage over the predators. But when we come to small tracts, where you can have quite a concentration of predators entering the woodland, in those situations it appears to be at a significant disadvantage. So for this species, large tracts of forest produce source populations, whereas tiny fragments of forest or little ribbons of forest along fields, although you might find some ovenbirds in those kinds of areas, they would be populations that would be very unlikely to maintain themselves over time. So they would be sink populations. Let's consider a variation on a theme now. Let's consider a situation like this. Here we have two young white-tailed deer. These are young of the year. You can tell by their white spots. Now, deer are famous among North American mammals for modifying their environment. But the reality is that many kinds of animals can do that. So, in the case of deer, if you have a large population of deer, deer browse on shrubs. So if you have a lot of deer browsing on a lot of shrubs, they are going to change the character of the habitat. They're going to kill some of the shrubs. They're going to prune back low branches of trees. They're going to make it a different environment by their feeding activity. This kind of a phenomenon is referred to as the ideal free distribution model of population dispersal. So it really is a subset of the source sink model, but it asserts this additional point, which is that organisms that live in a habitat can actually modify the habitat, and as populations grow, they modify the habitat further. And they can make the habitat deteriorate if the populations are very high. And that's what we see with deer. Now, in these two photographs, actually, I should point out, the last one was of the eastern white-tailed deer. In this photograph here, what you see is the western black-tailed deer. Here's a closer-up view of them with mother and baby here. Notice how big their ears are. Black-tailed deer are also often referred to as mule deer because their giant ears make them look kind of mule-like. So the idea of this model is that as populations grow within some habitat, the quality of the habitat is likely to decline. And so as the quality of the habitat declines, other habitats that previously might have been of secondary quality will start to look pretty good. And so animals will start leaving the deteriorated habitat to colonize the habitats that are now the highest quality ones. So we have one more model of population dispersion to consider. Look at this photograph, for example. Notice that we have an area of rather extensive forest on the right-hand side of this image, but then running along the base of this hill, we have a forest opening. Actually, what that is a power line right-of-way where all the trees have been cleared out. And the idea of this last model is what happens when different kinds of habitats come into contact with each other. So we have forest coming into contact with power line right away. We also have a little pond in this image, and way over on the left we also see a farm field, a hay field in fact. So what is it that differs about how forest occurs when it's next to a power line right away versus how is it affected by something like a farm field? These kinds of questions are included under the heading of the landscape model. And what the landscape model tells us is that not only do the organisms within a habitat influence the habitat's quality, but also the quality of the habitat is altered by what kinds of nearby habitats are present. So in this particular image, we can say that this low intensity use power line right away, where you don't have a lot of people in there, don't have a lot of kinds of activity in there, that is going to affect the adjacent forest in one kind of way. In contrast, that hayfield that gets mowed periodically and might have tractors driving around on it and people and possibly animals, domestic animals on it, that is likely to affect the adjacent forest in a different kind of a way. Of the two, it's likely that the power line right away has a more benign effect on the adjacent forest than does the higher intensity use agricultural land. By discussing these kinds of ideas, we're building up to talking about the topic of population dynamics, and that's what we will focus on for the rest of today. Let's first define a term, the term demography. That term refers to the study of population growth, so the change in population over time. And a simple kind of a situation that we see among simple kinds of organisms is that populations grow multiplicatively. In other words, by some multiple. So if we think of a simple example like one yeast cell, which divides into 2 yeast cells, which divides into 4 yeast cells, and so on. So the yeast cells are multiplying by a factor of 2. And even higher animals can exhibit some kind of multiplicative growth, especially at their early stages of population growth after they've recently colonized an area. And of course, this little bunny here, we often refer to rabbits as multiplying, and they are indeed quite good at that because they make lots of babies. The kind of growth that often characterizes recently colonized populations is one that we could refer to as exponential growth. Exponential growth is characterized by a continually accelerating rate of growth. If we look at this graph here, notice that the slope of the line increases from left to right. And if we carry that out to its ultimate extreme, eventually the line would go vertical, which in the jargon of calculus is referred to as reaching its vertical asymptote. What that would mean in terms of population growth is that at that point where it becomes vertical, population growth would become infinite, which of course in the real world can happen. But in the mathematical world, we can model that. So we can model with an equation of a form like y equals ax to the n, with n being our exponent, hence the term exponential equation. Now with respect to population growth, there's another term that we need to define. The term that's called the intrinsic rate of growth. Often symbolically we indicate that by the letter R. Now, under ideal conditions, where there are no brakes on the rate of population increase, R is referred to as the population's biotic potential, the maximum rate at which the population can grow at. In its simplest form, R is calculated by knowing about birth rates and death rates. So if we subtract the death rate from the birth rate, we have R, the intrinsic rate of population growth. However, there are also other factors that can influence population growth. If we have individuals moving in and out of a population, that's referred as emigration and immigration. And so we can also consider that in our calculation of R, where individuals that leave are subtracted from individuals entering a population. When we just have birth minus death rates to consider, then we're talking about the natural growth of the population. But when we also have to factor in immigration and emigration, now we're looking at the overall rate giving rise to R. So let's consider that y equals ax to the n exponential equation in a little bit more sophisticated format. Let's change those y's and all that sort of thing into variables that are more meaningful. Look at this rewriting of that equation in the upper right here. And let's consider what these different terms refer to. This is more in the form of calculus notation. So n sub t refers to the number of individuals present in a population at some particular time, and we can call that time t. The number at some point in time is going to equal the number of individuals in the starting population at time 0, so n sub 0, times e, which is the base of natural logarithms, and which by definition is 2.72. And then we're multiplying that by an exponent. And the exponent includes a factor for the intrinsic rate of growth, R, times time. Now, for those of you who've had calculus, you'll know that you can take this formula and you can find the slope of the line that it generates. But of course, because this is the slope of a curved line, it's a little bit more complicated. And so we have to do something called finding the derivative. When we find the derivative, we look at this equation on the lower part of the image. This is the equation of the slope of the line at any point on it. And we read this one as follows. dn over dt, that is a notation that comes to us from Leibniz. And most calculus courses use Leibniz's notation. It means explicitly a differential in n over a differential in t, which we can translate to plain English to say a change in numbers over time. So if we want to know what the change in numbers over time in a population is, we have to compute it by multiplying R, the intrinsic rate of increase, times the number of individuals in the population. This kind of an equation, by the way, that contains a derivative is called a differential equation. Now we can derive this formula, this derivative, even without resorting to calculus, just by using a bit of common sense and some diagramming. So let's go through the steps and see how we might do that. Let's start out by making a flow diagram, like you see in the upper right of this image. So in our big circle, we have the number of individuals in our population. And the number of individuals gets greater as a consequence of birth rates, which is symbolically b times n. And the number gets smaller as a consequence of death rates, which we can write symbolically as d times n. So if we take this diagram, we can then express it in English words in a sentence. And we can write a sentence like this. A change in numbers over time is the difference of the effects of birth and death rates on the population. If we assume, however, that the birth and death rates are constant. Usually when we try to develop a mathematical model like we're doing here, we use a number of simplifying assumptions like this. Now, of course, in the real world with real animal and plant populations, some of these simplifying assumptions don't work. However, when we're getting our first approximation of how nature works, often it's a very useful exercise to insert these simplifying assumptions. Now, the next thing we want to do is take our sentence and turn it into symbolic language, the language of mathematics. And so we can say a change in numbers over time, which again using Leibniz notation we write as dn over dt. Change in numbers of population over time is equal to the birth rates times the population minus the death rates times the population. And then using a little bit of freshman algebra, we can factor out the n and turn it into dn over dt equals n times b minus d. Now, we only need to do one more thing to come up with the formula that was on our last slide. We can remember that birth rates minus death rates is what is equal to the intrinsic rate of population increase, r. So we can simply substitute r for b minus d. And then voila, we have the derivative of the formula that we started out with on our last slide. Now let's descend into the wonderful world of logistic population growth. The logistic model is one that comes to us from moderately advanced calculus. It's the sort of thing that one learns about in semester 2 or even 3 of college calculus. But this is a very useful concept to use with respect to population growth. So we're going to learn a little bit about it anyway. And as we do, I think it will start to look a little less intimidating, even though it is associated with more advanced math. First of all, let's consider that in pretty much all naturally occurring populations, population growth doesn't continue unabated indefinitely. Eventually, population growth slows as individuals in the population run out of room and run out of food and things like that. In mathematical terms, that's called reaching a habitat's carrying capacity, which is symbolically signified with the letter K. If we look at the graph on the upper right, we see the red line there. That is the population's carrying capacity. And notice that although that graph starts out pretty much like the exponential graph in our previous images that we were looking at, as it approaches K, the rate of growth, the slope of the line, goes down. And this is what a logistic equation allows us to model, is a situation like that, producing that S-shaped kind of a curve. So if we look at the equation that relates the rate of population growth to carrying capacity, we can write it like this. Again, dn over dt means change in numbers over time in a population. This is going to be equal to the intrinsic rate of growth, which can also be described as the contribution of each individual to population growth, times the number of individuals in the population n. So up to this point, everything in blue here is exactly the same as it was with our exponential formula. Now we're going to add in a factor that relates to carrying capacity. And this we will write as 1 minus n over k. So this we can refer to, this factor in red, as the reduction in population growth rate due to crowding. Now we can also derive this logistic formula with some modest levels of logic. It is a bit more complex than the last one that we did, but it's still eminently doable if we just think our way through it. We also are going to have some simplifying assumptions here, and let's start with those. Let's assume that a population's reproductive factor, which we can write symbolically as capital R, and which we can define as the number of surviving individuals per parent, let's assume that this reproductive factor declines linearly, as it does in this graph on the right-hand side of the image. So, in other words, as population size increases, the reproductive factor goes down. And that makes sense. You'd expect that reproductive factor would be greatest when the population is small. Now let's go back to our old friend growth rate, intrinsic rate of increase, lowercase r. This is going to be maximized when population size is very small, when it's near zero. And it's going to be minimized when carrying capacity is reached. So at carrying capacity, at K, we can expect that each individual in a population will just replace itself, so that the reproductive factor at this instance is going to be equal to 1. So every time an individual dies, it's replaced by one individual, so population is no longer growing. So from the graph we can see that the rise, the increase in the y-axis, will be going from 0 to 1 plus r, r being the maximum rate of growth and the 1 coming from the level of growth at carrying capacity. The run of the graph is K. In other words, the x-axis. And so if we want to find the slope of this line traced out by the reproductive factor's decline, we can use a linear equation formula, our old friend y equals mx plus b, where m refers to the slope of the line and b refers to the y-intercept, the place where the line crosses the y-axis. And so now all we need to do is do a little substituting. So the rise over the run is simply r over k. That's the slope of our line. And the y-intercept is 1 plus r, the place where the graph crosses the y-axis. And so we can write a formula symbolically that looks like the one at the lower right of this image. Capital R equals minus r over k, because we have to put in that minus sign because the line is going down, not up, times n, plus the y-intercept, 1 plus r. Now, I think that is probably enough for today. Why don't we leave it at that point? And we'll come back to this with a fresh mind in our next program. We'll review what we've done with logistic growth, and then we'll complete our derivation of this formula.